Thanks, guys, for joining this tech talk. We've got our engineers from Oxford Flow to talk about their ES control valve technology, I guess is the right terminology. It's a tech talk which is going to be recorded. There's a Q&A at the end, and we will upload it to the InstMC YouTube channel. But again, thanks for joining, guys, and over to you, Jack. Take it away.
So yeah, just started off to say that sharing the call with a few other people. So my name's Jack Thornton. I'm a technical sales manager at Oxford Flow. So trained as an engineer, but kind of customer facing to help through with any proposals, making sure the solution we design is perfect fit for whatever we might do. But it means I get a lot of the interesting applications. So I'm quite well suited to talk about the control valve here. I've also got Mathew Lackie, who's our business development manager for a region. He's currently lost his voice, so I'm taking over for him. So if there's any queries in the future, then best place to direct anything towards him. So, did you say you'd like us to start off straight away, or hang about? Did you say? I missed that.
No, just carry on, Jack. Just go straight into it. Yeah.
Yeah. Okay. So first of all, a little about who Oxford Flow are. So we're a startup, or we were a startup rather, from Oxford. We've now got a whole host of investors. I mean, the big takeaway ones here that it's nice to see the big names off of BP, and there's this company called Energy Impact Partners, who's a combination of various investment. The investment arm of various companies, so General Electric and Schlumberger are two big ones to name a few. So they've seen our technology and they're pushing us forward. So it's useful to see some big names. We're not just we're not a nobody from Oxford. We've got some big backers who believe in us. Slightly more detail about Oxford. So like I said, we're based in Oxford. We're originally actually a spin out from the University of Oxford. Whether it's over 10 years ago, 15 years ago, but we've now grown. We're a mature company now. Our headquarters is, like I say, just outside Oxford, but we've got people based all over the country. So Mathew, who I just mentioned, is based in Aberdeen, but more worldwide than that as well. We've got a lot of channel partners and distributors basically in every corner of the world. The joke that I hear one of the sales guys say is we're represented in every country and every continent apart from Antarctica. So a little bit more about who Oxford Flow are in terms of what we're actually doing. So all of our products here that we've got, there's a core innovation behind. So we've looked at the current market, the incumbent valves. We've spoken to various customers and people in the industry, and we've asked what is the major failure mode, and we've looked to design that out with a blank piece of paper, fresh design. And we do this by looking at these kind of 4 principles, and they kind of all actually link to each other quite nicely. But the first one is simplicity. So most of the time we remove the major failure mode. We simply design it out. So we're not going for those incremental changes that you might be used to for other valves on the market, where each time you've kind of got a new innovation, but it's only a 2% increase in improvement or a 2% decrease in emissions. We've started completely from scratch and removed all of those failing design elements out. And that inherently makes all of our products incredibly reliable and resilient, because like I said, if you're used to having this failure mode, which I'll go on to in a small moment, that is you're having to replace components every 6 months, 1 year, 2 years. We simply remove those components from the design by using some quite clever innovations. And then finally, as a repercussion of these things, the fact that we're simpler and we've got fewer parts and less failure modes, the performance is drastically increased. And that's on multiple fronts. That's both on kind of the maintenance side, just as much on the kind of accuracy and performance side. So I was mentioning about their simplicity. So as 2 kind of examples on the right, we've got two of our major product lines. The top one is a self-acting regulator. That would traditionally have a large rubber boot or diaphragm, and by that flexing, that is what controls the outlet pressure of the regulator. Now that flexing component often fails, and when it fails, you've got a complete pressure loss. P1, you can have full P1 down to P2. There's also a lot of issues with control at the low and near end. Now, to talk to that simplicity element, we've removed that completely and replaced it with a rock hard stainless steel piston. Now that can't burst, it can't rupture, it doesn't flex in unpredictable ways. So we've drastically increased the lifespan of these regulators by doing so. And equally, the performance, because there's none of that flex that you might sometimes have at the low and high end that's slightly unpredictable, that stainless steel piston is not flexing at all. So we can be highly confident at operation at 0.1% all the way up to our 99.9%. Equally, the main topic that I'm going to go into today is this ES valve, which is on the lower right. That's an isolation or control valve. And traditionally, we have a large mechanical stem, which connects to the actuator and to the closure member. That's an external leak path. Again, we've just decided to completely remove that. I'll go into that in some more detail in a moment. So yeah, I've already got ahead of myself. So these are kind of our three major product lines. The ones on the left and on the right, using that same regulator piston technology that we've got patented across the world. And in the center, the isolation and control valves is this patented stemless technology. The stemless technology, as mentioned here, can be used in control valves or isolation valves. Actually, the design is almost identical, apart from how we configure the setup. And it's designed for single phase or multi-phase, liquids or gases, any combination of the two. So just to talk to some of the products. So this is the regulator actually first, but we'll focus on the regulator. This is an example where comes into my team where we're looking at how to really solve a customer problem. So we're problem solvers and engineers. A good half of the company are engineers actually, even if their role might not dictate them as such. We've come from that background, so we love solving problems. This is an example that Mathew brought to the table, an operator in the North Sea. It's got an overboard dump valve, fire suppression. It's got seawater flowing through it. And this valve, every time it was being tested, their rubber diaphragm was failing immediately. And the way the customer saw it is, well, we know it's going to work the one time there's a fire, but every time we test it, we're having to replace this. So that was causing a massive issue in their maintenance. So we've come to the table and we're displaying here our diaphragm-free regulator, that piston operated actuator, and that's really solved the problem. So now every time, well, it's not, again, there's no ability for it to fail. The stainless steel piston cannot rupture. So we've solved the customer for that. I know that two people I call Tony and Mathew worked closely on this. Is there anything else that you'd like me to say on that point whilst it's on the slide?
No, not really, other than the fact that we're going to actually talk about a little bit later on about this particular application. So it's worth bearing in mind how we solve this.
Yeah, one of the nice things about this regulator as well is it's a self-acting regulator on the pilot. But if you can see in the picture in the middle, we have also got an anti-cavitation trim in there as well. So now you've introduced where sometimes a control valve would be needed because of the trim capabilities. You have now got anti-cavitation trim with inside a self-acting regulator as well, which can also help reduce costs to the operators.
Yep. Okay. Thanks for that. Like I say, we'll probably come back round to it. And then another regulator here we've got is this. Is our this IMC. So this is a regulator that utilizes a standard globe style body, but we've rotated our technology 90 degrees and we've still got our piston, which is actuating in here. So as before, no diaphragm, your major failure mode has been completely eliminated. Your maintenance cycles are drastically improved, And as I said, that performance has actually increased because of it. The nice thing about this design, as per normal globe valves, is you can still release, access everything in line without having to interrupt the line, because this cartridge can just simply be lifted out. I've got some of our distributors in the States are currently competing about the quickest time you can do a full overhaul. Now, they're doing this in training, so I wouldn't suggest you do this in the real world, but they can get down to, I think their current record is at 7 minutes and 40 seconds. So that just proves how simple the regulator is, that we can do a full overhaul in 7 minutes and 40 seconds. If I move on to a control valve industry, so this graph points out that 60% of all fugitive emissions, so that's any emissions that are leaking out of the system unintentionally, are coming from valves. Now, that's massive. And if we break that down even further, we can say that 85% of that previous segment is all coming from the stem and the stem packing. So again, as I mentioned before, rather than incrementally improving your packing or adjusting your stem, changing your actuation package, the obvious answer to solve all this is just completely remove it. And that's what we've done with our ES series stemless axial valve. Now, this is the one that I mentioned that can be both in control valve or isolation variants. And this is how it works. So we've got a nice cut through here. All we've done is we've moved the actuation element inside the valve. So we have a hydraulic pack, which is considerably smaller than a conventional, or can be considerably smaller than a conventional actuator. That supplies hydraulic fluid on either side of this piston member here, and that's simply by adding or subtracting hydraulic fluid from each of those cavities, we move that whole piston backwards and forwards, and therefore the closure member opening and closing. I should probably point out that, well, it doesn't matter. In theory, this can be unidirectional, but it's designed to be flowing from left to the right. And because it's an axial valve, we've actually got the outer diameter of the internal flow path at the center is wider. So that means that the actual relative pressure loss across the whole valve is remarkably low, especially when comparing to traditional globe valves. Not quite the same as a ball valve, because a ball valve is full bore, but we're getting close to that element because the cross section at any point is relatively consistent throughout the valve. But the key part here, by us having the hydraulic fluid filling and moving this cavity, is we no longer have that mechanical linkage stem outside the valve. So we've completely eliminated emissions directly at the source. There is physically no way for this valve to have fugitive emissions. I might have got ahead of myself because, again, apologize. I thought this might have a animation, but the animation may not be working. Alas, all that happens here in the animation is it shows that this the closure member and the piston move backwards and forwards. That, I think the screenshots at different locations. So you can see here, this is at kind of, I don't know, approximately a 40% open position, and then here we've got the 100% open position. So as a nice kind of back-to-back comparison here, we're looking at a traditional quarter turn control valve. We're eliminating that mechanical drivetrain, as I mentioned, and that large actuator that needs to go on top. We replaced it with a small compact HPU, hydraulic power unit, and that can really, depending on the application, particularly in large valve sizes and large pressure classes, really reduces the size and the weight of the overall package that we're offering. One nice thing to say, I should go back at about the compact self-contained HPU, is that it doesn't actually scale with valve size. So we've been clever by the fact that we're only actually actuating a very small amount of hydraulic fluid, about the size of a Coke can. So we don't need a massive HPU. So this valve here, I think, is a 4-inch scan that we've got on the right here. But if that were to be a 24-inch, the hydraulic pack would be the same size. So the valve would dwarf the the HPU, rather than the actuator scaling linearly as it would traditionally. We can configure this in lots of different ways. That's the nice part of it, the engineering side, when I'm getting into it. So the previous one I showed you is what we'd call our double acting. So there's a hydraulic cavity on either side of the piston. In this setup, we're relying on a spring to revert the closure member to its closed position, and we're only adding hydraulic fluid on one side of the cavity. But otherwise, it works exactly the same. It's just we've now got a mechanical element aiding our closure. This slide is just to point out that just because we've got a new technology and a new valve, it doesn't actually mean that the way we go about sizing these things and deciding which valve goes into which system changes at all. So we can still offer all of the standard cages and trims and plugs that any other control valve manufacturer would be able to offer. Equally, showing you here that the CVs for reference in future, I believe actually these might have been tweaked slightly. They're slightly higher now, but either way, just showing that the capacity of the valve generally tends to be considerably higher than a globe valve. But that is my portion, or at least the initial portion over. I'd like to hand over to Tony Brooke.
Okay, thank you. Thanks, Jack. Yeah, my name's Tony Brooke. I've spent the whole of my working life in the control valve industry. My position at Oxford Flow currently is as a technical advisor. So I advise on applications, the challenges that we find in various applications around the world. Predominantly, I'm involved in oil and gas. But we also work in other industries that require control valves. So this little portion of the presentation is to actually look at the aspects of the ES control valve that has benefits for certain specific applications. There are such a myriad of applications we can't pick on all of them, but a lot of them have similarities that people watching this can actually probably recognise. And the first one, certainly to mention, is the zero gland emissions. So Jack's quite clearly covered that and why we're able to claim this, because of the lack of evacuating stem which travels through a gland into the valve itself. What I think is worth pointing out is that many manufacturers at new valve supply and testing, factory testing, can claim very high gland emission figures. So from a point of view, I mean, very high, very sort of tight glands when the valves are new, and the valves go off into the site. They get installed, they get used, and from that point on, the very tight gland emissions begin to deteriorate. There's a number of reasons why these deteriorate. Obviously, if a valve's operating, the stem is sliding up and down through the gland itself. You're going to get aspects of wear. You get easement of the materials. A lot of these gland materials are non-metallic, PTFE or filled PTFEs or PEEK, or this type of material, and you'll get elastic deformation of the gland components. But one thing that often isn't quite appreciated is that the control valve trim is converting a lot of potential energy in form of pressure energy into velocity, and in doing this, you get quite an amount of vibration within the valve trim components themselves. And as the trim component is connected directly to the valve stem, and the valve stem is running through the valve packing gland, then you will get failure of valve packing glands or deterioration in gland seal tightness simply through the operation of the valve and the vibration that gets transmitted to the gland system through the stem itself. So what the title of this slide is that we've got with our ES valve zero gland emissions permanently. It does not deteriorate with valve life because there is no stem, there's no seal to deteriorate, and this is exactly what Jack's been talking about when we talk about zero emissions. So they're permanent zero emissions, and I think that's a point worth bearing in mind. Typical applications that would require zero gland emissions. Clearly, carcinogenic chemicals, things that are poisonous or toxic to humans or wildlife or the environment, is a very, very high requirement for a valve such as this. Methane, toxic media, hazardous and sour gases that we find offshore with H2S inclusion, this sort of thing. Very, very important that we contain that. And other chronic gland leakage problems, even liquids that where the valve is suffering from vibration or high energy conversion, then by removing the gland you can also remove the risk of leakage. It might not be a toxic issue, but it could also be health and safety. You don't want oil or water, etc., spilling out onto the floor of the facilities. So that's the point there, that it is a permanent lack of emissions. Okay, Jack, if the next one, please. Footprint and weight, again alluded to by Jack earlier. The actuator itself does not scale with the valve size. The amount of hydraulic oil that we use goes up with the valve travel, but it's quite small, and typically we're talking about a can of Coke, that sort of size, for some of our even largest valves. So typically you can see the little picture there is a similar sort of size valve to a traditional control valve with a pneumatic actuator. So the footprint is much lower. The weight and handling issues that you get with the valve are much reduced. There's no conventional bonnet on the valve. The bonnet of a control valve is the closure member that fixes the actuator to the valve and also closes the pressure envelope of the valve body. We don't have that big, which is usually a large cast flange with a large boss in the middle of it. We don't have that as part of our design. So from the point of view of where weight and footprint is important, specifically FPSOs and offshore installations, there's a great gain to be had from removing those heavy parts, the larger actuators, and installing a much more compact self-contained unit, which is what the ES valves provides. Once more, Jack, please. This is something that may or may not be apparent, but the trim rigidity. What I'm talking about here is the fact that our control member, whether you call it a valve plug or a piston or whatever, is actually hydraulically locked in place. By far the majority of process control valves that you'll find on plants are pneumatically operated. When using pneumatic operation, it's either double acting or single acting against a spring. There is an amount of sponginess in the system itself. If you apply a load to a pneumatic actuator, because of the compressibility of the air that's been used to power it, you can actually shift the position of the actuator temporarily. The instruments and that are applied to the pneumatic actuator will bring the valve back into control, but that shift can cause upsets in the process itself. And can cause some amount of instability and oscillation. The ES plug, being hydraulically locked in place, is impervious to these pressure fluctuations and will not move due to a fluctuation of pressure, the outlet or the inlet of the valve, or other forces that might come from pumps. Typically, if a piston pump is being used, you tend to get pressure spikes as the pump is operating. Again, the ES plug is impervious to that type of pressure transient. So typical applications where this is important: water spillaway overboard into the caisson, outgassing, or sour gas stripping, such as rich amines, this sort of thing. Also flashing service. Typical would be a Joule-Thomson valve or a hydrocarbon condensate valve, where the liquid is changing to vapor over the valve. Fast-acting liquid control valves, gas riser exports, where we may get slugging, liquid slugs in a gas pipeline, all create forces on the valve control components, which can cause the valve to actually jump and move out of control. This doesn't happen in the ES valve. And I've actually, in the next slides, Jack, please. I've actually just highlighted a couple of three of the applications that I've just mentioned now, just to go into them in a little bit more detail. These used to be major problems for manufacturers, and still are major problems for manufacturers using pneumatic actuation. So in an application such as rich amine, which is where the solvent comes through the stripping vessel, taking out gases such as CO2 or any sour gases from the process. The amine, which is the solvent, passes through a control valve where its pressure is reduced to allow these sour gases to come out of solution. So you're actually bringing a liquid into the valve, and coming out of the valve is something akin to soda pop or some sort of gassy liquid. And when this happens, the change from liquid to this gassy sort of outlet fluid is instantaneous, and it can cause some real problems for stability of the valve. The massive increase in velocity that occurs, the change in pressure underneath the valve plug can cause the valve to jump around quite violently. And a lot of manufacturers that have these problems, their only solution to this is to turn the valve around and flow it in the opposite direction, which is not the way the valve's been designed to work, but it does solve the problem for a little while. Secondly, in the sort of diagram in the center, falling water columns. Typically, you'll find these on offshore platforms or even onshore facilities where a fire pump system or cooling water systems are being employed. In this particular one, it would be very typical of an offshore facility where the water pumps, the fire water pumps, are running continuously, and the positive and the water is being spilled overboard into the sea or into a caisson or something of that nature. With low flows, as you see on the diagram on the left, the water just trickles down the outlet and down and the downpipe towards the sea or the caisson. As those flows increase, the pipe becomes full. and you will get a siphoning effect. Sometimes these down legs can be from anything from 10 meters to 30 meters, and you have a siphoning effect of about equivalent to that head of water. And this will create a pull, a suck, if you like, on the valve trim components that can break up, and suddenly that negative pressure is released, and this causes a lot of instability in the valve itself. Again, by utilising the ES valve, and this is the particular application that Jack showed earlier, where we were actually able to utilise one of our regulators, both in the regulator and in the ES valve. That control component, the valve plug itself, is hydraulically locked and cannot actually react to the pressure transients caused by this siphoning effect. And the third and last one, any sort of liquid flow control valve or pressure control valve, there exists in the control valve selection procedure a risk of something called bath plugging, and you can feel this for yourself if you have a sink or a bath or some vessel that has one of the old-fashioned sort of bath plugs with a chain on it. If that bath is full and you lift that chain and bath plug out of the sink hole, and you just try to let it back in carefully and gently, it will grab it from you as the pressure above the plug overcomes the flow pressure below the plug in the drain, and it will continually pull that from you, and it's quite a pull, even with something like 1.25 inch diameter plug. Well, this happens in control valves as well. So if you've got a valve flowing liquid that's been asked to close fairly rapidly, or or the trim components are not balanced efficiently, when you try to control close to your seat, you get the exact same bath plug-in effect. And the actuator and the instruments will try to work against it and will lift the plug again, then it will bang back down again. And the effect is rather like something like a pile driver. It is absolutely terrifying when you see this occurring. It probably will cycle close to open 2 or 3 times a second, and the whole pipe starts to shake around. It's quite frightening. I've seen people actually run from valves that start to bath plug. And again, the lack of the pneumatic actuator and the solidly locked hydraulic valve plug will help. Will eliminate the effect of bath plugging. So that's one of the benefits that we have there. Jack, if we can move on probably to the last few slides now. We've already mentioned capacity, so I can move fairly quickly with this. If you consider the flow path through a conventional globe valve, you can see that there are a number of right angle turns, sometimes even more than right angle, to get the fluid actually through the convoluted valve body shape. Each one of those turns results in a loss of head. If you then compare it with a simple little diagram of the ES valve just to the right in the green there, which is an extract from one of our CFD outputs, we don't have any of those turns. So all of that head loss, all of the head that would have been lost in a conventional control valve, globe control valve, still is available to for flow, for producing the flow through the valve. So the capacity through the valve tends to be generally much higher than a globe control valve. This helps with maybe debottlenecking processes. So if you've got, you're looking to increase capacity of valves, not wanting to make big piping changes, typically mature wells where production pressures have dropped, then quite often this extra capacity size for size will allow you to fit the same size valve and increase your production by, I don't know, maybe 30% or so, without having to change valve pipes and increasing valve sizes. So it's something worth bearing in mind, that the axial flow valve may well save quite extensive piping costs. Jack, the next, please. Okay, and again, debris tolerant. The little picture on the left there is a photograph of I think it was something like a 12-inch valve on a gas transmission pipeline. The pipeline is renowned for high concentrations of black powder. And this is a feature of gas transmission pipelines the world over. It's a process where the gas actually reacts with the pipeline material and creates this black amounts of this black powder, which travel with the gas, and of course tend to sort of collect wherever there's an interrupt in the flow. And you can see, hopefully you can see that valve is, the level of the black powder is right up to the valve seat, so it's completely blocked, 50% completely blocked. Given the axial flow geometry of the ES valve, that would pass straight through. There's no way for it to actually stop, settle, and block. So, by far, sand laden, separator level control valves, black powder valves, heavy oil with asphalt inclusions. Also possible advantage where calcium carbonate or sulfur scaling takes place, where fluids tend to sort of slow down and deposit. So very, very debris tolerant in its geometry. Jack, again, please. And because of the lack of the turbulence that the globe valve bodies create, we also can claim a much lower erosion potential. So where we've got applications that may be high in erosive inclusions, such things as high sand content, this sort of thing. If you look again at and consider the geometry of the flow through a globe valve, you can see many places where there is an impingement onto the actual pressure containing parts of the valve valve body and the valve bonnet. These two pictures, by the way, the left-hand side is looking down into a globe valve, and you can see where there's actually a hole in the bottom of the valve there, where the fluid carrying sand has eroded totally eroded the bottom of the valve body away and created a pressure breach, and therefore reportable to HSE and all of the problems that brings. The second one on the right hand side is the actual lower portion of the valve bonnet, the closure member that sits on top of the valve, and because of a seal failure in the valve trim, the fluid's been allowed to flow upwards into the underside of that valve bonnet, carrying sand with it, and has caused major erosion of the lower portion of the valve bonnet. If that would have carried on, it's likely that the actual sort of strength of the bonnet would have been very, very compromised, and may have even have caused the bonnet to actually split open. So both of these pictures, by the way, are from the UK North Sea, and this is current. These things are happening as we speak today. Moving further on with that, Jack. So the valves we were looking at there are level control valves on oil and gas separators. Due to the amount of sand that comes through from the wells, the two valves at the bottom, the water outlet and the oil outlet, suffer from a lot of sand inclusion. Typically, it's the next slide, please, Jack, straight through. Typically, the water outlet valve sees most of this sand, and the water that we're talking about here is produced water. It's gassy water. So as soon as we start to flow the water through the actual control valve itself, this gas comes out of solution. It causes the volume of the fluid to increase. That means it has to go faster through the valve. It's taking with it sand. And so the type of erosion that we saw earlier with those two bonnets, that's how that gets created. By utilising the ES valve with its streamlined straight through flow geometry, we can avoid that type of erosion and the safety issues that brings with it. The oil valve itself will also have some sand. Sometimes that sand goes all the way through to the mole pump, the main oil line export pump. Sometimes it doesn't. It depends on the well and the amount of sand that it's producing. But wherever we're going to see this type of risk of body erosion from sand, black powder, asphalts, this type of thing, the ES valve does have benefits because of its geometry. I think that's the last slide from me, Jack, if I'm correct.
Yeah, that's correct. Yeah, it was anything else you wanted to say before I moved on?
No,
to
I think that's
summary
me done. Hopefully, we might get some questions later that we can come back to. Thank you.
Yeah. So just thought I'd put a bit of a summary slide up. So again, this is the valve. Here's some real photos. Obviously showing that they're not just the animated ones. And inside here, you can see kind of various trims and actually the actuator that we've been talking about. So just a brief overview. So 2 to 24 inch. 24 is kind of isn't actually a hard limit as such. The design and the concept is scalable. It's just kind of that's the area that we see most interest. Class 150 up to 2500. Temperature ranges, as you can see, fit soft and metal seated options. So that generally tends to be the soft seated for isolation valves if you want a really tight shut off. But again, we can configure in any way possible. It's kind of the real story here is that everything is configurable. So all of the parts we can swap out for alternatives, however we see fit, to really suit the application, as all the applications, for example, that Tony's just been going through. This just speaks to you quickly about the hydraulics. So I mentioned about there's a HPU that sits on top. So we have the ability to use any supplier of HPU. So if there's a specific supplier that is currently on site or is used frequently, to make sure that we're kind of being consistent, it doesn't matter. All we need is a powered hydraulic power unit. Sorry, a hydraulic power unit to supply hydraulic pressure into the valve. So here's a few different examples, but they always tend to be quite small, as per I was mentioning earlier. One thing I didn't actually necessarily mention before, but this is the enabling technology. So because we've got no mechanical linkage, we can't report back the valve position in the same way that we traditionally do by looking at the stem position or rotation. So we do this by having a patented magnet sensing component that's embedded inside the valve in a non-pressure element of the valve. Then when that whole closure member and piston assembly moves backwards and forwards, we can track based on the magnetism angle how open and closed the valve is. And that's incredibly accurate depending on the valve size, obviously, but we can get that down to 0.1%. And with position, all of the other benefits that Tony was just mentioning about how we're kind of hydraulically locked as well. So we're not going to get any hunting as such. Not necessarily hunting, any wobbling of the position. This is just to point out that we've passed basically every test under the sun, because we're the new kids to the block. We get asked to do even some more tests that kind of aren't even adhered to here. So this is just a small selection, I'd say. The fire test one always looks impressive, but with any certification or requirement we've probably already achieved that you might have. This is just to end on a nice point about the, just before I go into the kind of deployments and where we're in the field, just to really show that if we're looking at the emissions side of things, really show the scale of the problem here. So as we said before, if we're based on those two graphs I had before, essentially 50% of all future emissions is coming from the stem. And that's the size of the problem here. So 58 million tons and $1.5 billion per annum. It's a real simple solution. Just remove the leak path. So that's what we have to do here. This is just a selection of some of the points we've got. So again, pointing out that the variation, some are control valves, some are isolation valves, all over the globe. So we've got the North Sea, we've got North America, this is in Chicago, the Middle East, and so on, and Malaysia as well here. So just pointing out some. If you need any more information or about any of these in more detail, contact us and we can see what we can provide to give you some more confidence in the technology. So this is my final slide. So just to really hammer it home, we've got less moving parts, no stem, we're small and lightweight. All of that design choices mean that we're now got increased performance and reliability, and we're fully in compliance with EU methane regulations because there is no leak path. So that is enough from me. I didn't know if Mathew Lackie wanted to say a little closing statement.
Yeah, no, thank you very much for that, Jack. Thank you, June, for the talking for me when I've got the man flu. But yeah, it's a couple of things I wanted to point out on this as well to everyone is all this technology, especially the ES valve, was never actually designed to be zero emissions straight out the bat. This was all designed on advice from the oil giants around the world who were fed up packing stems. They wanted a stemless valve because of stem failures and the costs associated with it. So we designed a valve with no stem. But the main things and the main principles around this was the performance and the reliability and the lifetime extension between maintenance. But designing out that moving part, we've made this completely zero emission as well. So, which is an added benefit to have. Which is fantastic. But yeah, no, thank you very much for that, and thank you very much, Tony, for your section as well around the applications. It was I thoroughly enjoyed that. I never get bored of hearing all these ones from yourself and your experience. So yeah, thank you very much. And if there's any questions.